道的题。Today we will introduce 7.3 and 7.4. Okay, 7.3 and 7.4. And 7.5, 7.6 we will not introduce. Okay, so today we will finish chapter 7. Okay, we will finish chapter 7 and the last Tuesday. Okay, so last Tuesday I will give you an examination for last Tuesday left. Okay, from 8 p.m. to 10 p.m. Okay, last Tuesday left. From 8 p.m. to 10 p.m. we will test chapter 6 and chapter 7. Okay, so chapter 6 and chapter 7. Okay, so last Tuesday left. Okay. At the beginning, we will record the content of the last class. Okay, last class. So here, first we can see that this is done. Okay, so letter H be a solid bounded by a two perpendicular plates, perpendicular to the x-axis at x equal to a and x equal to b. Okay, so if for each x in the interval AB, okay, in the interval AB, so the cross section area of x perpendicular to x-axis is AX, then the volume of the solid is V equal to the definite integral of AX from A to B, okay, from A to B. So here, this is the formula, okay, this is the formula. So, and then we introduce the solids of evolution. The solids of evolution. So here we obtain let f be a continuous function and a non-negative function on closed interval AB, and let R be the region that is bounded above by y equal to fx, below by the x-axis, and undersized by the lines x equal to a and x equal to b. Find the volume of the solid of revolution that is produced by revolving by the region R, okay, about the x-axis. So this is the problem. Okay, so what is the formula? So the formula actually is V equal to the definite integral of pi fx square from A to B, okay, from A to B. So here actually is the y equal to fx, okay, we were looking about the x-axis, okay, what is the x-axis? So actually here actually for each closed section actually is a circle. It's a circle. So the circle, the rulers actually is fx, yeah, the fx. So here actually means, so actually the pi fx square actually this integral, okay, this integral actually is the area of the closed section, okay, closed section, okay. So here this is the formula, And now, and this class, okay, this class we will introduce is the same, okay. So here is y equal to fx. Y equal to fx. So we know that if y equal to fx, this curve, okay, this region, okay, this region R, okay, this region R. If this region R revoluting about the x-axis, okay, so we have the volume V actually is equal to the definite integral of pi fx square from A to B, okay, from A to B. So this is the revolution, okay, this is the revolution about x-axis, okay, about x-axis. So now, if we revolution the region R, okay, about the y-axis, okay, about the y-axis. So here So here, if we revolution about y-axis, okay? So if we revolution about y-axis, so what's Vy? Vy equal to what? So Vy equal to what? Okay. So now this is the content we introduced this class. Okay, this class. So here, so we can see we have this problem. Let f be continuous and non-negative on closed interval a b. Here a less than b. Okay. Let R be the region that is bounded above by y equal to fx, and bounded below the x-axis, and undersized by the lines x equal to a and x equal to b. Okay. So find the volume of the solid of revolution x, capital X, that is produced by revoluting the region R about the y-axis. Okay, about the y-axis. So here we can see if we revoluting the region R. Okay, about the y-axis. About the y-axis actually is solid lattice. Okay, solid lattice. So here for this short, okay, for this short actually is a short like is a tube-like, okay, tube-like. It's a tube-like, okay, it's a tube-like. So now we need to find the volume of the solid of tube-like, okay, of tube-like. So for this, so here first we need to find the volume of the cylindrical shell, okay, cylindrical shells. So here we can see actually here we have a shell, a clean shell, okay, clean shell. So here. So a clean shell is a solid enclosed by two concentric right circle cylinder. Okay. The volume V is a clean shell with interluders. Interluders are 1, okay, and outerluders are 2, and height h. So here the volume V can be written as V equal to area of closed section times height. Okay. So here we can see. Okay. So the closed section actually is what? Here is a circle. Yeah. So here a circle with luders are 2. Yeah. And here is a circle with luders are 1. Okay. So here actually the closed section. Okay. So the area of closed section actually is pi times R2 square. Here this is the area of the outside circle, okay? Yes. The area of the outside circle. So we need to minus the area of the inside circle, okay? So here minus pi R1 square. So here this is the area of the inside circle, okay? So here, so this number, okay, so this number is the closed section, okay. So closed section times what? Times the height, okay, times the height h, So here this number actually is the volume of, so the volume of the cylinder shell. Okay, so cylinder shell. So here we can see here is pi, we can move it. So we can take it out. So pi R2 square minus R1 square times h. Okay, times h. So here R2 square minus R1 square. Okay, R2 square minus R1 square. Actually, we can write it in pi R2 plus R1. Okay, R2 plus R1 times R2 minus R1, okay, and times h. So here R2 plus R1. Okay, we can write it in this 1/2 pi. Okay, we times 2 and we divided 2. Okay, so here is 1/2 pi times. Oh no. I'm sorry. Here we times 2 and divided 2. So here we can write it in 2 pi times half. 2 pi times half R2 plus R1. Okay. And times R2 minus R1 times H. So here we can see here 1/2 R1 plus R2, okay? 1/2 R1 plus R2, this is what? So actually for here, this is actually the average rulers, okay? So the average rulers. So here actually is the rulers of the outside circle plus the rulers of the inside circle. So we take half, okay? We take half. So this part actually is the average rulers, okay? The average rulers, and here R2 minus R1, okay? So R2 minus R1, this is what? So now we can see here R2, okay, R2 minus R1. So actually here is also R1, okay? So here this is R2 minus R1, actually is distance, okay? Distance actually is the thickness, okay? It's the thickness. So here means the average rulers times the thickness times the height, okay? So times 2/2 pi, or times 2 pi, okay? So this is what? So this is the So here, this actually is the volume of the cylinder shell, okay, cylinder shell. So means 2 pi times average rulers, okay, average rulers times height, times thickness, okay, times thickness. So this is the formula of the cylinder shoulder. So from here now we can see we use this formula, okay? We use this formula to find the volume of the revolution, okay? The revolution about the y-axis. So it's the same, okay? It's the same. The first step is we need to divide the AB, okay? Divide the AB into n subintervals. So here means we divided the distance, okay, into n subintervals. So the solid can be divided into what? So here now we can see here. Now so the underlying idea is to divide the interval AB into n subintervals, okay? So thereby subdividing the region R into n strips, okay? R1, R2, Rn, okay? So here, the first step, we divided AB into n subintervals. So we obtain the n strips. The first strip is R1, the second is R2, the third is R3, okay? The last one is Rn, okay? So the first R1, okay? So the first R1 strip, okay? The first R1 revoluting about the y-axis, okay? About the y-axis. So here we can obtain the first tubular, so S1, okay? S1 and R2, okay? R2 is the same, okay? So revoluting about the y-axis. So revoluting about the y-axis, so we obtain the second tubular solid, S2, okay? The second tubular solid, S2. So and R3, okay? And R3 revoluting about the y-axis. So we obtain the third tubular solid S3, okay? So and the last one Rn, okay? The last one Rn we revoluting about the y-axis. So we obtain the last one tubular solid Sn, okay? Sn. So here, when the region R is revolution about the y-axis, these strips produce tube-like solids, okay, S1, S2, Sn, okay. That is the next one inside the other, okay. and together comprise the entire solid X. So here the volume of the solid can be obtained by adding together the volume of the tubers, that is V equal to the volume of S1 plus the volume of S2 plus the volume of Sn. Yeah? So this is easy to understand. Yeah? And now, as a rule, so the tubers will have curved up the surface. So there will be no simple formulas, okay, formulas for their volumes. However, if the strap are seen, then we can approximate each strap by a rectangle, okay, by a rectangle. So here means here this is the Rn, okay, so this is the Rn, so this is the n subinterval. So here from here we can see actually we can approximate the area of the strap. Rk actually we use a rectangle, okay. We use a rectangle to approximate the case strap, okay. So these rectangles we are revolving about the y-axis, okay. So we are produce cylinder shells whose volumes correctly approximate, okay, the volumes of the tubers produced by the original straps, okay. So this sentence, I hope you can understand. Actually here, so actually this is the strap. So this strap revolving about the y-axis, so we can obtain a tube-like solid. And we need to find the volume of the tube-like solid, okay? But actually we can use a rectangle. To approximate the straps. So the rectangle is also can revolving about the y-axis, okay? The y-axis. So now we use the volume of the rectangle or the revolving of the rectangle, okay, to approximate the tube-like. The volume of the tube-like, okay. So we will show that by adding the volumes of the cylinder shells, we will obtain a Riemann sums and approximate the volumes B. And by taking the limits of the Riemann sums, we can obtain integram for the exact volume, okay, for the exact volume. So here now let's see the step, okay? Now let's see the step. So it's the same, okay? So the first step actually is the partition. So the step 1. So the partition, okay? So the partition. So here means that the first step we divided, okay? So here we divided AB into n subintervals, okay? Into n subintervals. So here we can obtain this n subintervals actually is x0. X0 actually is A, okay? So here we can obtain the n. We can obtain the rulers x0, x1, x2, x3 is xn minus 1, xn, okay? So xn is B, okay? So we can obtain these rulers, and then actually we can obtain the first subinterval x0, x1, okay? x0, x1, and the second subinterval x1, x2, okay? And go on. Actually, here is xn minus 1 to xn, okay? To xn. So for each subinterval, we can find the y's, okay, or the y's. So delta x1 equal to x1 minus x0. So the second, okay, so the second is delta x2 equal to x2 minus x1, okay. So go on, here is delta xn equal to xn minus 1, okay, xn minus 1. So this is the first step. So the second step is the summation, okay. So the summation. So step 2, okay. So step 2, so is the summation. Summation, okay. So for this summation, actually here is now we can see for each subinterval, okay. For each subinterval, so here the volume. So here for each subinterval, so we can obtain the n straps, okay. So each straps revolving about the y-axis, so we can obtain the n tube-like solid, okay. So for each tube-like solid, okay, actually we can obtain. We use the rectangle to approximate, okay. We use to approximate the strap of the area of the strap. So here we can obtain the first one, okay. So the first one here, this is the case. No, let's see this, okay. So for the first one here actually is. For example, here is x0, here is x1, okay? Here is x1. So this is the first strap, okay? So the first strap here, and this is the y-axis. So this is the x-axis, okay? So this is the x-axis, this is y-axis, okay? So this is the first strap, okay? So the first strap, so here. Now we use the first strap revolving about the y-axis. So here we need to find the volume of the first tube-like solid. Okay, so the tube-like solid. So first here we choose one point. Okay, we choose one point. Here we denote it by x1 star. Okay, and we use the y's of delta x1 and the height fx1 star. Okay, we use this rectangle. To approximate the strap. So the same. Okay, so we use the solid of the rectangle revolving about the y-axis to approximate the solid of the tube-like solid. Okay. So here now we can see for this rectangle we revolving about the y-axis. Okay, revolving about the y-axis. So what's the volume? Okay. So what's the volume? So the volume actually we use this formula. Okay, equal to 2 pi times the average radius. Okay. Times the height, times the thickness. So here now we can see the average. So the average radius is what? So here we have that V1. Okay. So V1. Okay. V1 actually approximately equal to here. So the average radius. So the average radius actually is, we know that the inside radius actually is x0, yeah?
Yes.
And the outside radius actually is x1, yeah?
Yes.
So what's the average radius? So the average radius actually is x0 plus x1 by 2, yeah?
Yes.
This is the average radius, yeah? And so what's the height? So the height is what? So the height actually is distance, yeah? So this is the function at the point x1 star, yeah? So this function times what? Times fx1 star, okay? fx1 star. So this is the height. So what's the signature? So the signature actually is what? Is this length, yeah? So it's x1 minus x0, yeah? So here this is x1 minus x0. So this is this is the first one, okay? So the volume of the first one, okay? So here now x1 minus x0 actually is delta x1, okay? Delta x1. So here actually equal to 2 pi times x0 plus x1 by 2 here, and fx1 star and times delta x1, okay, times delta x1. So it's like this, okay, so it's like this here. Here. Now let's see. So here, okay, so actually here, this is fx1 star, okay, this is x1 star, actually we take the so fx1 star, actually we take it as the midpoint, okay, so like this, here we can see, if we let xk star be the midpoint, okay, so to be the midpoint of the interval xk minus 1 to xk. And if we construct a rectangle of height fxk star over the interval, and then evaluating this rectangle about the y-axis, produce a cylinder shell of the average radius xk star, height fxk star, and thickness delta xk, okay? So from 1, so the volume Vk of the cylinder shell actually is 2 pi times xk star times fxk star, okay, times delta x. Okay. So here actually he takes the x1 star as the midpoint, okay. So here means what? Here means x1 star equal to 1/2 x0 plus x1, okay. So here actually we can evaluate this. This actually is 2 pi xk star times 2 pi times xk star times fx1 star. Here is x1 star times here times delta x1. Okay. So here is choose x1 star, the midpoint of the first subinterval. Okay. So it's the same. The second. Okay. So the second subinterval we also choose the midpoint. Okay. The midpoint. The third take the midpoint. So the last one take the midpoint. Okay. So here, from here we can see the first one is 2 pi x1 star fx1 star and delta x1. Okay, so this is the volume of the first duplex solid. Okay, so the second actually is 2 pi x2 star fx2 star. Okay. So times delta x2 plus the last one. Okay, so the last one is 2 pi x n star fxn star times delta xn. Okay, times delta xn. So here we can write it in the summation sign. Okay, so the summation sign. So here is actually the summation of 2 pi xk star times fxk star times delta xk, okay? So yk runs from 1 to n, okay? So the volume, okay? So this is so the volume actually V approximately equal to this number, okay? This number. So now this is the second. So this is the second step summation. So the step 3 is taking the limit. Yeah? Taking the limit. So taking the limit actually is v equal to what? V equal to limit the delta max delta xk approaches 0. So the summation of 2 pi xk star fxk star delta xk, okay, delta xk yk runs from 1 to n, okay, yk runs from 1 to n. So here actually equal to, the definite integral of 2 pi x fx dx yk runs from a to b, okay, yk runs from a to b. So this is the formula, okay, so this is the formula. So here we can see the volume, okay, so the volume by cylinder shells about the y-axis, okay, about the y-axis. So let f be continuous and non-negative on closed interval AB. Let R be the region that is bounded above by y equal to fx, below by the x-axis, and on the sides by the lines x equal to a and x equal to b, okay. Then the volume V of the solid of revolution that is produced by the revoluting the region R about the y-axis is given by V equal to the definite integral of 2 pi x fx from A to B, okay, from A to B. So here, now, actually here, so the integral line 2 pi x fx. So what's the integral line? What does this function mean? Okay, what does this function mean? So actually we have it's like this. Okay, so now informal viewpoint about the cylinder shells. Okay, so the volume V of a solid of revolution that is produced by revoluting a region R about an axis can be obtained by integrating the area of surface produced by an arbitrary cross section of R. Take parallel to the axis of revolution. So here now we can see this is the region. Okay, so this is the region R, and we choose a line. We choose a line here. This line. Okay, this line. And we use this line revoluting about the y-axis, okay? Here, now we can see in the interval plus the interval AB, we choose 1 point x, and so here we can open a line, okay? So we open this right line, okay? So this right line revoluting about the y-axis, okay? About the y-axis, actually we can open this. We can open this shape, okay? This shape. So here we can see this revoluting about the y-axis. So this actually here this is a circle. This is a cylinder, okay? So what about the circle of the cylinder? So the circle actually is the radius actually is what? So the radius actually is x. So here the length of the length of the circle, okay? So the length of the circle actually is 2 pi x. 2 pi x times the fx, okay? So 2 pi x times the fx actually is the area of the cylinder, okay? So the cylinder. So here now we can see 2 pi x. 2 pi x actually is what? 2 pi x actually is the length of the cylinder of the bottom circle, okay? The bottom circle. So the bottom circle, the length of the bottom circle, okay? And fx is what? Fx is the height, okay? It's the height. So here now, I think that if you can understand it, I think it will be better. If you can understand it, so you just remember it, okay? Yes. 2 pi x fx. Okay, so here now we give an example. So here, use the cylinder shells to find the volume of the solid produced by the region. The region enclosed between y equal to the square root of x equal to 1, x equal to 4, and the x-axis. Okay. So this is the region. Okay. This is the region. So the region is revolving about the y-axis. So first we plot the revolution. Okay. So we plot the region. Okay. So y equal to the square root of x. So y equal to the square root of x, okay? So y equal to the square root of x, we plot it. We plot it, so actually it's like this. So here is y equal to the square root of x, the square root of x, okay? So x equal to 1 and x equal to 4. So when x equal to 1 is here is 1, and x equal to 4 is here, so it's 4, okay? So the region actually is this region, okay? So this region, yeah, is this region, yeah. So this region revolving about the y-axis, okay? Revolving about the y-axis. So here actually we use this formula, yeah. Yeah. So we use this formula. So here fx equal to what? So here in this formula fx equal to what? Equal to square root x, yeah? Yes. Equal to the square root x. So here actually is the revolving b equal to the definite integral of 2 pi x fx. Here fx actually is the square root x. So the square root of x dx. So from what to what?
From 4 to 1.
From 1 to 4, yeah? So here is from 1 to 4, from 1 to 4. So here, dx. So we just need to find the definite integral of this definite integral, okay? So here 2 pi is a constant. We move through the definite integral sign, okay? So the integral sign, so here actually is 2 pi, the definite integral from 1 to 4. Here, the square root of x actually is x to 1/2 power, yeah?
Yes.
So x times x 1/2 power is what?
X 3 over 2.
X 3 over 2 power, yeah?
Yes.
So dx. So here we need to find antiderivative of this function x 2 by 3 power. So here actually is 2 pi x 3 by 2 power plus 1, yeah? By 3 by 2 power plus 1. So this is this function is the antiderivative of this function, yeah?
Yeah.
So evaluate at 4 minus evaluate at 1, okay? And so this is equal to what?
2 over 5 x to the power 5 over 2.
So here now we can compute it here. 3 by 2 plus 1. So actually it's 5 by 2, okay? So here equal to 2 pi x 5 by 2. So here is 5 by 2, by 5 by 2. So here is by 5 by 2. So here is 4, here is 1. 5 by 2, okay? So 5 by 2, 1 by 5 by 2. So actually it's 2 pi 2 by 5, yeah? 2 by 5 and here is x 2 by 5 by 2 divided at 4 minus divided at 1. So here actually is 4 pi by 5, okay? So here is 4 5 by 2 minus 1 5 by 2, okay? So 4 5 by 2 power is what? 4 5 by 2 power actually is 4, okay? 4 5 by 2 power, we can divide it by 4, 1/2 power to the power 5, yeah?
Yes.
4 1/2 power is what?
2.
2, so it's 2 to 5 power, yeah?
Yeah.
2 to the 5 power is what?
32.
32, yeah?
Yes.
So here is 32, here is 1, yeah? 32 minus 1.
31.
31. So 4 pi by 5 times 31. So the result actually is 124. 124 pi by 5. Okay, by 5. So this is the result. So this is the result. So this is the first one. Okay, now let's see pages 315. Okay, 315. So here now we do an exercise. See pages 351. Number 1. Okay, 351. Number 1. Okay, number 1. Y equal to x squared. Okay. Y equal to x squared from 1 to 2, okay? Revolving about the y-axis. So here, so this area, okay, y equal to x squared, y equal to x squared from 1 to 2, okay, so this part revolving about the y-axis, we need to find the area, okay, or we need to find the volume, okay, so do it. Do it. So just use the formula, okay? Use the formula, okay? So have a break. 10 minutes.